Good afternoon. We begin again, and this time I'm going to complete my two lectures. One lecture is just over. The second one is going to be on FMEA. And in this, we take a look at how we can predict the rate of failure of certain products. These could be finished products, or these could be, for example, a process. So this is quite often utilized right at the design stage. Right at the design stage itself, you'd like to do FMEA to try to make sure you can take all those preventive steps to look at the manner in which a product or service may fail. The outline of this our talk is going to be what is FMEA, a little bit about the history of it, what are the benefits, what will be the applications of FMEA. This is something you'd like to be able to see. The procedure for doing it, I'll give you a glimpse of the worksheet which is there, and a couple of examples and a summary. This is what my plan is for this session with you. What exactly is FMEA? It's a technique to try to improve system performance or to try to design systems that would resist failure. Both of those are achieved by doing FMEA. Why do you do FMEA? Well, first of all, let's try to understand the definition and the purpose and the benefits and so on. I should just caution you that FMEA is a team approach. It generally cannot be done by just one person trying to work out the details of it. Something we got to remember is the whole purpose for FMEA is basically try to reduce the impact of failures. And in doing that, what it really does is prevents a lot of crises. If you would not do FMEA, then the design or the process would be released as is without any kind of prediction of the chance that it might fail. It may fail to function as required, or it may fail to deliver the function the performance that is again expected of it. That is something that would be there if we do not do FMEA. So FMEA is kind of a preventive, predictive technique. That's what it does. And it leads to actions. It leads to actions that will lead to improvement in performance. What exactly is the result? Well, there are two dimensions. Whenever something breaks down or some failure takes place, there are, generally speaking, two or three things that happen. So I'm going to show you that slowly. The first thing, of course, is there is the severity of the impact. That can be high or low, depending on the nature of the feedback, nature of the failure that took place. You might get some feedback saying that the impact was high or the impact was low. The other aspect is the probability of it occurring. That again can be high or low. So if you got a situation when you've got a high probability of failure and the impact is large, in that the adverse consequences lead to things that you do not really want, then you've got a high risk situation, and that is that red area there. If you look at the picture there is that red area, and that actually says if my product ends up there, if my process ends up in this area, I've got to make every effort to either reduce basically the likelihood, so I should try to push it down this way, or I should try to take some preventive steps so I can reduce the impact. The whole idea is to shift a process or a system which is here more to this side. As you go from here to here, basically you're trying to reduce the impact, also trying to reduce the likelihood. And this is achieved by doing FMEA. This objective is achieved by doing FMEA. Let's take a look at the output. What exactly happens at the output? Now, if we look at the system for a couple of minutes, you'll find there are certain components in the system that has gone through, this particular system has already gone through some kind of FMEA analysis. So the component names are given there, the components that make up the system, then failure modes, in what different ways could that component fail, for example, loose wiring or a failure of a plug or something like that itself. What are the causes of that failure? It could be vibration or something else, that also is pinned down there. Then the effect of that failure. Causes of the failure would lead to, and then again you've got something called the effect of the failure, then the correction of the problem. What are things I can do to try to reduce either the impact or the likelihood of that thing? And then I put some general comments there. And this is what I do with every component that makes up the system itself. So this worksheet is going to be the output. At the end of your FMEA analysis, you'll end up with a worksheet like this. And of course, in addition, you'll also end up with some priorities, because you could do many different things. And the FMEA approach the FME approach also tells you, it gives you a sorting of priorities. It tells you what are the things that you must take some steps to try to prevent now, try to take some corrective action now. What are the other things that could probably wait, and you'd probably take some time to figure those things out and probably take some corrective action. But the ones that have high likelihood of failure and also have a high impact, those actually are the ones that should be addressed as quickly as you can. When you do that, you're really following a structured approach. You'll identify the potential failure modes. You'll basically identify what different ways could this system fail. You assess the failures to determine the prioritizing actions. And this is something that we got to be able to do, because you must attack the more important ones first. Then, of course, once you've gone through the analysis, you've got to document the process. You've got to make sure you release the action items to those people who are supposed to be able to act on this. FMEA is intended to basically rate the severity of failure modes. Failure modes are those different ways by which a product could fail or a service could fail. Identify actions to reduce the occurrence. This will to impact the likelihood itself. And of course, test the adequacy of controls. You might have some control actions put in place. You'd like to probably check them out in that the control actions themselves do not fail. This is something you'd like to be able to do. Some history of FMEA. It was created by the aerospace industries in the 1960s to try to make sure that there were not as many failures. And flight is something that can lead to a loss of life. That's something very, very costly, and you'd like to avoid as much as you can. And of course, the loss of the equipment, that also is something you'd like to minimize. Ford began using this in the automotive area to try to reduce breakdowns of cars. And it was adopted by the big three when they moved slowly toward QS 9000. They started using FMEA. The big threes are the GM, the Chrysler, and Ford. These are the big three automakers. They started using FMEA. And the Automotive Action Group, Industry Action Group, this is a group that basically formalizes a lot of actions which are going to be there to benefit the companies, to benefit these three auto companies there. So what are the benefits of FMEA? Safety is something that you get out of this. You improve quality and also improve reliability. All those three things you basically impact. If we continue with the benefits, the potential benefits can be potential. Now those are the previous ones for the real benefits. Now there are some potential benefits. The company image may improve. User satisfaction is also something that might also improve. Lower development cost, because if you've already done FMEA, it probably puts you at a higher ground sort of. And also the presence of a historical record. This is also something that's like a benefit. You'll find out how did I reach certain decisions during design or in the development stage. What all things did I go through to try to do this? That comes very handy when you're trying to do the same job again. You've got a history there. And the applications where you can apply FMEA is concept development, when you're just basically trying to conceive a new product. That's like one place you could probably use FMEA. Design FMEA, this is called DFMA. This is DFMEA. This is one place where FMEA can be very, very effective, because you are really trying to prevent, before the new product comes along, before the new design is converted into a manufactured product, you're trying to predict as much as you can about the likelihood of its failure. This is something you'd like to be able to do as much as possible. And of course, process FMEA. So many processes that break down in process. And you'd like to be able to see, can I reduce the likelihood of its failure or its impact? This is something you'd like to be able to do. Now, more and more, services are becoming a very significant aspect of our economy worldwide, globally. And services can also fail because of a variety of different reasons. So we are also getting into now doing FMEA for services, and of course equipment. FMEA is done for there also. If you're looking for a procedure, you got to start at the component level. And you'd like to see what are the functions of each of these parts, and sort of try to come up with some sort of a basis to say that the product or the component may fail in this manner. This is something you should be able to do. If you continue with the procedures, you determine the effects of those failures there. This is something you'd like to be able to figure out. And then, of course, the severity. What is the impact and what is the likelihood? Both of these things you got to figure out. as much as possible, whatever it is you're trying to improve. It could be, for example, the cover of this. It could be the cover of this CD. This could fail in certain ways. It may actually damage the disk. The disk is inside, and if this design is not right, it may actually end up damaging the disk. Or it may just come off the locks. It may come off the hinges, for example. Or it may crack, or it may scratch the disk, and so on and so forth. So many different ways. This cover itself could really lead to a failure of the total system. So you'd like to basically understand the different ways it could fail. That will be the mode. Then you'd like to make sure what is the likelihood for this happening, and then what is going to be the impact. And then will I be able to detect? With that, you'll probably work at various components. For example, you might look at the hinge, you might look at the cover, you might look at the plain surface there, the finish of it, and so on and so forth. That little paper that is there, for example, some paper is there. Can that come off? Can that actually interact with the disk in any manner at all? When the disk is put in place, it should not, the surface underneath should not probably touch the bottom of the thing. So, in fact, there should be some design modification right there. You may not be able to see it, but there should be some projection there that holds the disk. It's a very delicate thing. It should be held there in the right place, And it should be portable also. I should be able to carry this in my suitcase, for example, or in my briefcase. Or sometimes I stick it right with my laptop, and I carry it across town and so on and so forth. So that's also something that this guy should be able to prevent. My loss is going to be loss of data, loss of the disk itself. That's going to be my impact. And what is the likelihood? This is something we've got to figure out. And if there are actions required, then of course we'll modify the hinge or modify the stand or modify molding or do something there to try to do this. This is something we should be able to do. When you do it all, eventually you got these numbers there. You've got the likelihood and you've got the impact. These should be quantified. Then you've got something called detection probability. You should be able to detect that there is a problem there. That also is part and parcel of doing FMEA. You multiply these three quantities, which is the probability, the impact, quantified, and the detection capability. If you multiply these three, you'll end up with something that is called the risk priority number. If you end up with something that's like, if detectability is low, obviously it's more serious. So you'd like to give it a rating that's high because it's got poor detectability. These are things, when they're multiplied together, you end up with something called the RPN, the risk priority number. And risk priority number basically helps you to try to prioritize the different actions which this particular design deserves. For example, you'd have RPN for the hinge, you'll have RPN for the surface, you'll have RPN for various things, and then that would give you a hint as to what should be the priority in which I should be able to do it. You could even do FMEA for your glass, for example. Various ways you could damage this glass. Never mind breaking it, but when you just lay it on a surface, for example, could the glass get scratched? Could that impair my vision, for example? Could it collect dust and so on and so forth? So those are some of the things you'd like to be able to predict as much as you can right in the design stage itself. So there is almost nothing that should escape your FMEA. You end up with something that we call the worksheet. Here's an example. Here's an automotive company, and that has got an auto assembly plant, and it's got a paint shop that has got a tank, and this tank holds different types of paints which are required to paint the vehicle, the surface of the vehicle, for example. And there's some sort of automatic system that fills up the tank, the paint tank. Then it clicks, and then the automatic spraying starts, and so on and so forth. That thing goes on. Now, one could actually ask, in what different ways could the function be impaired? So if you look at the worksheet now, the function is fill the paint tub. Nothing more and nothing less. Just fill the tub. Failure mode is that the high level sensor never trips. Even if the the tank got full, the high level sensor did not trip. What is the effect of it? The result of this failure, liquid spills on customer floor, for example, the user. In this case, this painting machine has been supplied by somebody else. The car manufacturer does not produce this painting system. So it has been produced by somebody, and it's been mounted there. It's been installed there. So the auto manufacturer is really a customer. If paint spills over, it will fall on the customer's floor. So that's like a consequence. That's like an effect. What is the severity? And the severity is rated on a scale that's like between 0 or 1 and 10. 10 is, of course, very severe. In this case, the engineer, he sort of felt, looking at the damage and the cleanup required and so on and so forth, he gave it a rating of 8. He said if there are frequent failures like this, that would really end up probably shutting down the production line. What are the causes? What could have caused this? Now I'm getting into that fishbone diagram. You might remember we had a little diagram called the fishbone diagram, where we had the effect at the end and we had various causes leading up to that. That fishbone diagram is a brainstorming tool by which you basically, people who are working in that area, they would know very well what all different things could contribute to this failure there. So that's something that I'll be doing there, and I'll be tracing down to the causes. And the occurrence rating, this is something that of course is the likelihood, how likely it is to be, and they have given it a low rating. That means it's not very likely to fail there. The current control is based on the fill to the low level sensor. There's a low level sensor. The moment the low level sensor indicates that the tank is empty, or this paint tub is empty, it starts pouring liquid. It starts pouring. It should stop the moment level gets to the right level there. What is the chance of detecting that the level has been, the tub has become full? That detection probability, they've given it a number of 4. The capabilities have rated it 5. And of course, how critical is it? Is it critical or is it non-critical? Now, critical is something that can lead to a loss of life or loss of property. Hopefully, those things are not happening. Just some mess on the floor, so that can be probably cleaned up. Not a big deal there. So it's being regarded as something that's non-critical. If it is critical, action has to be there now. Then, of course, you multiply 8, which is severity, times the likelihood, which is like 2, which is 16, multiplied by detection capability, which is 5. You end up with a number that is 80. 80 is the RPN for this particular item there. Now, this RPN is the number that will indicate how important it is for me to fix this problem there, this potential problem there. It's going to be, now this 80 is to be compared to other things that might have probably picked up an RPM of 20, 30, 40, or maybe 200. We do not really know what all different things can go wrong in this plant. So that is something we got to figure out. But before that, of course, we got to do the RPN for every kind of function that can stop because of various types of failure there. Then what are the recommended actions? Recommended actions are perform the cost analysis of adding another sensor, halfway perhaps, between the low and high level sensors. That's like a recommendation because that's going to reduce the likelihood. And who's going to be responsible for it? There's an engineer, Mr. Ravi Kapoor, and he was told that as of 10th of October 2009, kindly get this fixed. And then this got filed, this worksheet got filed, and the report we have back is the action was taken, and the problem has been fixed, and they have taken this corrective action, which is like they have installed a level sensor that is halfway between the full and the empty positions. So this is a worksheet. This worksheet basically helps you identify what could go wrong, find out its impact, find out its likelihood, find out its detection capability, and then work out something called the RPN, which is going to give you a relative importance, relative significance of fixing this problem as opposed to others. And then, of course, the preventive action or the corrective action, and then assigning the responsibility for taking the corrective action to someone and reporting back on saying. So just see how we have prevented a potential problem. And this generally, these turn out to be high return projects. Their ROIs are pretty good. And this is just basically a flow chart of what we went through. Assign a level to each process or system component, which we did. That was the paint job, paint tub. List the function of each component. We also did that. It's supposed to fill up the thing, list potential failure modes. We did that. Describe the effect of the failures there. We did that. We describe the failure severity. That also we did. Spill on the floor and so forth. Determine the probability of failure. We did that. And the detection rate. Detection rate was also something that we did. Then we ended up with the RPN, and then of course we took action to reduce the highest risk. That's something that we did. What exactly is FMEA? If you get into the nuts and bolts of this a little bit, there are two key things that you must go after. One is the failure mode. Any errors or defects in a process, design, or item, especially those that affect the customer, can be potential or actual failure modes. These are the different ways the functionality can be harmed in some way, or it can break down. And the effect analysis is the consequence. Effect analysis is basically the consequence of something has broken down, what has been the impact of it. These two things you got to keep in mind. How has it evolved? If you go back to 1940s, for example, that's when the army started first using this. The US Army started using FMEA or some variation of FMEA. Then, of course, from that point on, if you take a look at today, there was a serious application of FMEA which was introduced by the Ford company in the 1970s. They had a large number of accidents with their Pinto cars, and these led to loss of life and loss of property. And there they did FMEA, and they located certain aspects of the design that had not been properly addressed when the design was commercialized. So this is like something that the results or the action items emerged out of FMEA, doing FMEA. FMEA is also used to try to improve production. You may have ongoing production going, you may have an existing design, that also can be done. Who are the different people who use this? All kinds of people: aviation people, nuclear power people, aerospace people, chemical industries, automotive industries. They've been doing it for a long time. And the goal really is to try to prevent accidents from occurring. That's really the goal. There's an FMEA cycle. And if you look at step 1, it is detect a failure mode. Try to find out what different ways can a product or a component or a service break down. So detect the failure mode and look at the severity. Look at the severity of it, which is like what could be the impact. From that you'd get to know the severity of it. What is the likelihood of it, and what is the detection number? We saw all of these things when we worked at the worksheet. Then you work out something called the RPN. Once you have the RPN, it can help you prioritize the actions, the corrective actions, as opposed to working on something else and getting your system improved. There are certain terms which are used in FMEA. There is something called FMEA. It is the manner in which the failure is observed, and the effect of the failure is basically the consequence of the failure itself that is there. Then there are other things. For example, there could be local effect, end effect, and so on and so forth. But there is the important one, which is the severity. It is the consequence of that failure. Basically, it is the worst potential consequence of a failure. And that is determined by the degree of injury, property damage, or system damage that could ultimately occur. That is like something that tells you how serious could this matter be. And let's try to see the manner in which a system fails. What exactly is something called the failure mode? Let's take a look at an example. In how many ways can a particular, let's say a vehicle, can stop functioning? Engine is not working. And partial function is, so there could be, that's a mode of failure. Engine is not working. Or not all function of the engine. The engine starts but it quits. So that means not all functions are properly working. So these could be the modes. These could be the different manners, different ways by which a vehicle would have difficulty getting going. If you look at other examples, for example, there could be technology mode. The failure could take place because of technology. For example, if there is a spacecraft flying and the onboard computer fails for some reason, that's a critical failure. There could be conceptual failure, and this can happen sometimes when a person does not fully understand how to carry out his task. And this happens a lot. This could happen, for example, I'll give you a couple of examples. One is, the people who are at the flight deck. They are the flight controllers, for example, at the airports. There are certain training that they have to go through. The other kind of people who also have to go through this kind of training is people who do weather forecasting. They forecast these different, they look at pictures, and from that, with their training, they can figure out there's going to be a massive storm, or snowstorm, or tornado, or something like that. That's something they're trained to do. There could be a conceptual breakdown there because the person's training is not complete, or some aspect of it was not covered very well. So there's a conceptual breakdown there. Of course, there could be organizational failures also. For example, you may not have well-defined job roles, And the result is that also people probably do not understand mission priorities. And the result is this: there is failure in salary administration because you penalize someone because he hasn't done some job. The problem is probably his job, the responsibilities and the roles, they were not defined very well. Whose failure is this? It's not the person's failure. It is actually the organization's failure that led to this kind of consequence. This is something we got to be able to do, got to be able to fix. If there's a weakness in design, if there's a weakness of the design itself, if the design of the cover is not good enough, I'll probably have a problem there. I'm showing you an example here, which is like a design defect. Look at the two parts of it. These are parts that are supposed to fit together. Now this is the polar connection. Polar means there is a positive end that must go into the positive hole there. There's a negative end that must go into negative plug that must go into a negative hole there. If they're of equal size, you know and I know that there's every chance that someone is going to connect it backward, connect the plus to the minus and the minus to the plus if the design is like this. So that can lead to a massive failure. That can lead to a disastrous failure, tripping and everything else, and fire perhaps, and so on and so forth. Change that to this system. Look at this now. The plus has got a bigger plug and it's got a bigger hole there, and the minus has got a narrower plug and a narrower hole. There cannot be a misfit there. There just cannot be a misfit by doing. The plus is not going to go in there, and the minus is not going to be easy for it to be pushed in if this can't go in there. So this is something that's going to prevent a misconnection, a wrong connection. This is like we look at a modification. We had this design to start with, and we changed that to this design, which is the modified design. And this actually is a way by which I'm converting an old design to a new design, and it will turn out to be a good design in the end. Failure mode, it could result in what we call an effect, and it is due to what we call a cause. These are the couple of things we got to remember. We got to remember that with every failure mode we have an effect and also we have a cause. It is the effect is something that actually results from it, but the causes are the ones that cause the failure to occur. So we got to identify these things. We got to understand these things. Take a look at another example. A piece of text is unreadable, and that leads to the customer not being satisfied. And this could be because of a variety of different things. Perhaps the writing surface was not smooth. Perhaps other problems were there, and so on and so forth. That's why the text was not readable. So there is the effect which is here, dissatisfied customer, but it was caused by this surface roughness. So there is the effect and there is the cause of it. It is due to this. And many times, of course, you'll be able to fish this out. You'll be able to basically figure out what caused what if you construct the fishbone diagram, and you do something in a very disciplined way that is called brainstorming. The only thing you do there in brainstorming is you do not control the number or the different diversity of the ideas that come up that are given by people. This is something you do not try to control or do quality check on. Let it pour out, and then hopefully some gems will also emerge as a result of brainstorming. So the fishbone diagram is a great tool to try to do brainstorming and basically figure out many different ways by which this failure could have taken place. So FMEA can lead to brainstorming. This is something you'd like to be able to figure out, and some procedure is given here. You can follow this or you can follow any other one. My favorite is to start with the fishbone diagram and to try to populate the diagram by asking people many different questions. And you could use the what we call the post-it notes, so you could do anything else. There are a number of alternatives available, and basically what you should be able to do is let the ideas pour. And there are some steps that are provided here: step 1, step 2, step 3, step 4, and so on and so forth. Eventually the idea is to be able to sort out the roots, to be able to get to the roots. Once you've got the roots there, you got a starting point. You can actually, if you're now looking for prevention in trying to reduce the occurrence itself, or perhaps the impact of it, if you trace it down to the root, you got a chance. You got a good chance there. And so brainstorming would be like one great way to get there. Now that will give you the cause. You also have to find out what is the probability that the failure will occur. This is something that can occur at various different places. There could be a very high chance of failure in which case the chance is something that I have to worry about. So I look at the ranking, and if it is very high, that will lead to a very high RPN, and I want to give it some attention. I want to, so basically it's going to be helping you in trying to prioritize the different action items. If something is likely to happen, if some failure is likely to happen, please go after it. Don't leave it alone. And then of course you've got to look at severity also, and severity or the impact of it, that can be done this way. You look at the severity. If it's a safety failure, it belongs to class S. If it's unacceptable, industry calls it class A. If it's a big risk, relatively big risk, and correction is recommended, it will be class B. There's minimum risk, that will be class C. And if you are willing to live with it, it will be class D. So these are the different ways by which I categorize my severity. And of course, numbers could be applied here. I could probably say 10 for S, 8 for this, and 6 for this, and 4 for this, and 2 for this. With that, I'll have numbers, and those numbers come very handy once I go out and I try to do basically what we call RPN calculation. So what are the various possible actions I'll be taking? If you look at the possible actions, I'll try to eliminate the failure, or I'll try to reduce the effect of it, or I'll try to reduce the occurring. So either I eliminate it altogether by taking some design action or by rectification action, or I try to reduce the effect of it. I take some preventive steps there, or I reduce the occurrence. Any of these things, if these are done, they are going to impact your RPN, and that's going to be a big plus. If you look at again the different alternatives that we've got, corrective actions we've got. When eliminate the failure mode itself, that means I just remove the root, wherever the problem started with. I minimize the severity. This could be another way to try to reduce the impact, reduce the chance of it, and improve detection. Any of these things, if you act on any of these fronts, you're going to be gaining. And lo and behold, we are back with the worksheet here, and I see there this item 80. This is the same paint tub filling problem, and it's got a RPN of 50. Hopefully, the other failure modes have led to an RPN that is less than this. Therefore, this is the one that should get some action. Some action is planned here, and this resulted from looking at severity, looking at the likelihood, and looking at detectability. And this is a non-critical item, so I don't really have to work on it immediately. But it is something I should take a look at, and that's assigned to an engineer. And the report is that yes, he acted on 10th of October 2009 and took the corrective action there. I've provided you here with a worksheet, and of course you'll find worksheets either on the internet or you'll find it in reliability books. And what I'd like you to try is, again, going back to the bicycle problem there. We did an FTA on your bicycle. Now this time try to find out, can you do an FMEA on a bicycle, on the total system as a bicycle? And just for one moment I would like to ask you a question, and the question is this: are the two wheels of the bicycle, as far as reliability goes, are they in parallel or are they in series? Please try to figure out the answer. Industry uses FMEA very extensively, and basically, this is something that is done very routinely, and has been prompted by the Automotive Industry Action Group, AIAG. They have basically prompted people to do FMEA, and you'll be doing design review. That is like something that is done. That's like another mode of doing FMEA, the design FMEA. This leads right into our design failure mode and effects analysis. Now we are looking at designs themselves, and we'll be following the same routine that we did for basic FMEA. Identify all the ways in which the failure can occur. And this, of course, we are trying to do this when we got the design on the drawing board. Estimate the effect and the seriousness of the failure and recommend correct action. And the corrective action here is going to be a modification of the design. So again, design failure mode effects analysis. This is going to be first identify the failure modes, look at the different effects of failures on customers, for example, look at the severity, look at potential causes of failures, and then look for modification of the design to try to eliminate this problem there. So details of doing FMEA, those are laid out in these different slides there. Again, I've got the failure mode there, I've got the causes there, I've got the effect there, I've got the correction there. And I've got to make sure that this is done in a team manner, because it's not so easy. Let's take a look at this example there. There was a particular storm. There was a huge storm that even brought a tornado with it. Unfortunately, the people who were watching the storm, they failed to recognize something called the mini supercell that was being formed in the storm system. They failed to recognize this because there was a shortage in their training. And this is something that became a major issue. Because the consequence was this: yes, there was some loss of life, because it was not a very teeny-weeny storm. It turned out to be a big tornado, and it led to loss of life and property. Although it was not, fortunately, not very big, but it was something that people should have caught early on. And this was missed because of lack of training, lack of comprehensive training. So that was pointed at something that was here. If you look at the design of the total system, what is the total system here? It is the man plus the system, all the communication devices and display devices and everything else, and the sensors and so on and so forth, and the data analysis programs and so on. All those things together, they make it the system. At the end of the day, it's the person who makes that decision. And if he's not competent enough to process all these things, that could lead to a failure. And this particular failure was traced to a problem that occurred with incomplete training of the person who was in charge of forecasting storms. Here's another example of a design defect. An engineer, this guy, he was riding a train and he failed to notice a red signal due to fog. And this led to a major accident, a loss of life and so on and so forth. Now this led to injuries and loss of life and of course damage to equipment. So we saw the cause. The cause was that the person could not see the red signal. And this was done by manually checking. He was looking out and he would check that way, whether the signal is up or down, or is it red, or is it green or something. He just couldn't see anything because of the fog there. And he might be coming from a different line. He might not be familiar with that area there. So he might not be looking out to see the signal, from far enough distance to be able to stop the train or slow it down. That he could not do. The corrective thing would be here to do not depend on manual detection. Try to see, can you provide some technology whereby this signal up or down, signal green or red, could be detected by going there. This is something that we should be able to do. And what we should really do is, as much as possible, we should try to see if we could prevent problems like this. The bottom line is going to be again calculation of the RPN. So this is something we'd like to be able to do. We'd like to work out the components of the RPN. And again, the risk priority number, it's made up of the severity, there'll be a rating, there'll be a number of the probability of the event taking place, and the detection capability. These three things, they must come together, and they should give you, if they give you a high RPN, that's a serious matter. You've got to take some action there. You've got to take some corrective action there. And these numbers come out as the result of this FMEA analysis. So I've got here the same formula there. S is the severity, O is the occurrence of failure, which is the probability, and D is the detection capability. These things together, when they are multiplied, you end up with RPN. RPN is the risk priority number, and that basically, if you got RPNs on different actions there, you should really go with the RPN that's got the highest RPN. First attempt that one, then go to the next one, then go to the next one, and so on. And with each of these RPNs leading up to some corrective action, that's really what you're after. So you do your FMEA in such a way that you're able to find these high impact, high likelihood, and low detection capability items first. Once those are taken care of, then you move down to the next ones and so on and so forth. This is something we should be able to do without any trouble at all, if I'm doing FMEA. So the summary of conducting FMEA: a cross-functional team must do FMEA, identify functions of each component, try to find at least one mode of failure, one mode of potential failure, define the effects, look at the severity, and look at the detection capability. This is something that you've got to be able to do. Once you've done that, you can calculate your RPN number. RPN would come very handy in terms of prioritizing the different number there. Once you've done that, you then got to be creative. You got to then come up with solutions, and solutions would come from engineers. To try to improve performance, how do you actually do this? Either you'd like to eliminate the failure mode itself, if somehow something is there that breaks down because of that. Minimize the severity of it, that's also something that's like another course of action that is there. Reduce the occurrence, reduce the likelihood or the probability of it, and improve detection capability. Like in our case, for the railway signal, it was not being able to see the red light, the red signal. That was like the problem there. So you try to improve that by putting in some technology that will probably, there might be some sort of a, not necessarily audio, but some other kind of signal coming through, and that should be detected automatically, in addition to whatever the person is trying to do. That should be there. But some failures are more preventable than others, and this we have seen so many times. Let's take a look at that warning system again. Notice here, we had that supercell. Supercell was formed in the storm system, and this led to a conceptual failure because the person did not have enough training to be able to do it. How could I change that? I could really change that by changing the technology. Perhaps I could use a different kind of technology and not be dependent on a person. Not be dependent on a person to be able to recognize that, because he's doing a lot of signal processing in his mind. Through his eyes, he's trying to detect some very fine things. Should it be left like this? I mean, look at the consequence. Look at the loss of property, loss of life. Look at the tremendous cost that would lead to. I could perhaps upgrade technology, and this is something we should all try to do. This is like one place where it's not very difficult to figure out what I should be doing right. You just should not hesitate to take that corrective action. That's the message. Basically, doing just FMEA is not enough. You should be able to take prevent the failure and loss. This is something for which you got to act, and that's something that comes along very handy once you try to do this. In certain situations, you'll try to quantify hazards, and I'll give you an example. If you look at the hazard scoring matrix, this is like another matrix. That's also very similar to what we did. We calculated RPN, and what this guy is doing, what this matrix approach is doing, it's ranking the severity in terms of the consequences: catastrophic impact, major impact, moderate impact, minor impact. So he's got some ratings there, and then you've got probabilities. And if it's frequent and it's catastrophic, you give it this, and if it's frequent and major, you give it this number, and so on and so forth. And if the probability is pretty remote, pretty infrequent, it's a minor sort of severity, you give it number 1. So here I've got items here that actually have a hazard scoring that is 16 or 12 or 9 or 8 and so on. If an item ends up, if my FMEA leads to this sort of scores on the hazard scoring matrix, this is like another approach. In place of doing the RPN, you could do it this way, and you'd again end up with very similar analysis. Here's an example which is using a decision tree. So what it says is, let's say first you've done this, and then you've got a number there. If the hazard score is 8 or higher, you move this way, and you try to sort of see, does a control measure exist for the identified hazard? If it is, you've got your action done. You don't really have to go further, just activate that action there. If it is not, then you see if you could improve the detectability of that particular thing there. And then you proceed to what we call a hazard guided FMEA. This is something that you should be doing. If you have good detection capability, just go ahead and act. There is no real issue there. If suppose it is not a high rating, let's say rating like 3, 4, 5, 6 and so on and so forth, then you come down this branch, and then you ask yourself the question, is this a single point of weakness? If it is yes, then you probably go through the other boxes and so on. If it is not, you stop right there. If it is not a single point of weakness, you stop right there. Stop basically means you got to move on now to other actions that are possible there. So what I would suggest is try to look up some references on hazard guided failure mode and effect analysis. Here's an example. This is this example is taken from the healthcare industry, and it turns out that there are certain patient alarms which are they are connected to the patient. If there's a patient in ICU, for example, you don't really have a doctor or a nurse sitting there round the clock and watching every movement of the patient or his BPs or everything else changing there. That's not something that you do, but you've got alarms You got the body alarmed in various ways, and those alarms trigger action. So basically what we do is, in certain places, would like to probably provide care, obviously, and monitor alarms. These monitor alarms would lead to the kind of actions that we would like to see. We got to make sure the alarms function. The alarms do not themselves break down. And for this, I'll probably have to go into this a little bit to make sure that the alarms are functional. I can rely on those alarms. I've got 3 there, action item number 3 there. 3A will have one consequence and 3B will have another consequence. In 3A, periodically I check the monitor status, just to make sure that the alarm is active and the alarm is still looking at the person there, and so on and so forth. And of course, the other part is the respond to alarm. That's also something I should be able to do once the alarm is there. So periodically checks the monitor status. So has there been an alarm? And now this step could fail if the nurse failed to check this status. That of course is something there, or misread or misinterpreted the alarm that came along, or partially checked. Any of these things could lead to a failure there. Obviously, I would like actually to get to this point when it's like I respond to alarms. And what are the different ways? Even if there was an alarm, the person probably did not respond. This happens once in a while. Or he responded slowly or too late, and by the time the patient was out of control. I mean, this is like something we should be able to do. Now, to try to get into this, you do an FMEA. To try to prevent those sort of occurrences, you get into this. So I have here 3B1, which is like, if you look at the first there, 3B1 did not respond. Why could he not respond? Ignored the alarm, did not hear the alarm, or the alarm volume was too low, or it was in a remote location, or probably the caregiver was busy and therefore just missed the alarm. And you do exactly what we did earlier, and you come up with outcomes. We come up with outcomes and action plans and so on and so forth. So we are also doing here what we had done earlier. We are doing something very close to FMEA. That's what we are doing there. Here, if you see, I've got the failure mode, which is the cause. Look at the severity, look at the frequency, and look at the actions, and look at the outcome. These are exactly the steps that we followed in the earlier case at all. Now, there's some slight differences between root cause analysis and so on. There are some similarities and there are some differences there. People tend to prefer one to the other. It all again depends on the industry. Engineering people, they tend to go by FMEA, and healthcare people, they may go by the hazard FMEA. That's like something that is there. We got to recall that FMEA is a tool. It allows you to prevent basically system, product, or process problems before they occur. FMEA reduces cost by identifying system, product, and process improvement opportunities in the early development cycle of the product itself. And it creates a more robust process. That is something that it does. It prioritizes actions to try to decrease risk or failure. And it also helps us evaluate systems and design from a new vantage point. This is the point of view of trying to take a vantage position of prevention. This is something that we try to do. FMEA is, of course, a systematic process, and we've gone through the steps earlier. And so you basically try to evaluate, you identify, you evaluate, then you try to quantify, then you try to prioritize, then you plan on some actions there, and you document the activities so these can be followed up later on. Purpose and benefits, there obviously are pretty major benefits of doing FMEA. This is something that's because of its logical nature, and it is done quite frequently. It's done quite frequently to be able to take care of this. Benefits of FMEA, again, I've repeated this, I've mentioned this before, I repeat it again. It leads to higher reliability, better quality, increased safety, enhanced customer satisfaction. It also leads to cost savings. It also leads to what we call continuous improvement. And there are some examples. There are some examples there when it says if it costs 100 when it is discovered in the field, that's a pretty high cost. It may cost $10 if it is discovered during final test. These are like the product development life cycle stages. It may cost only $1 if the problem is discovered during incoming inspection. There's like before you took that part and you assembled it in a complete system there. So it looked at your transistors or the chips and so on before they entered the system. And it's even better if you can do this, all this right at the design stage itself. So start your design, start your FMEA right at the design stage itself. And this is called DFMEA. What are the tools available to be able to do this? There's benchmarking available. There may be other people who are doing this job better. Customer warranty reports that can lead to failure indices and so on and so forth. Design checklists or guidelines, field complaints, internal failure analysis, internal test standards, lessons learned, return materials reports, expert knowledge, and certainly warranty service. These are the sources from which you can find out how different things can go wrong, in what modes do they fail, what is their impact, what is their likelihood. All these things can be found if you've got a good database. What are the possible outcomes? What if you would do FMEA? You can discover the failure modes, and it can lead to meeting certain legal requirements that also can be there. Duty cycle requirements can also be impacted. Product functions obviously can be impacted by doing this. Some of the key product characteristics, those can be enhanced by doing this. And certain product verification and validation. Validation is the actual use. Verification means it conforms to specs. And of course, to be able to do FMEA, you've got to do your P-team meeting, which is like guys would be sitting around and they would be basically getting briefed on it. And here's a little example. Perform DFMA. So the team has been now asked to, we are trying to design a new pressure cooker. And what all things could go wrong with this. And for that, you'll start your basically approach, determine the scope, what is it that we are trying to do, gather background, reference material, and so on and so forth. I'm going to give you one or two illustrations on this. Create block diagrams so it's easy to understand what the process is, what is actually going on. Identify team members, prepare the agenda, schedule and milestones, and of course identify item functions, failure modes, and their effects. This is something we should be able to do. For the pressure cooker, safety valve releases pressure before it reaches dangerous level. This could be like this is its function. These are the safety functions. It could fail because if this, for some reason, if the safety valve does not release, that could lead to a major explosion. Thermostat opens circuit through a coil before temperature rises above 250 Celsius, and this also is a dangerous situation. So the thermostat, so the safety valve could fail, or the thermostat could fail, or the pressure gauge is divided into green and red areas, and danger is indicated when the pointer is in the red section there. Now there could be a problem there also. So you can actually see three modes of failure right away. Define the scope. That means let's take a look at these systems there, and you could look at the electrical system, or you could look at the safety valve, thermostat, pressure gauge, whatever you want to. Focus, your focus is going to be safety. And for that, you again start with the block diagram, which is like the pressure cooker, safety valve, pressure gauge. These are subcomponents of it. It's like your FTA. This is very much like your FTA. The electrical system could fail because of heating coil failure or cord failure or plug failure there. And the safety valve could fail because of valve spring not functioning properly or the valve casing not functioning properly. There are certain assumptions you make. You make sure that the components that I've used, those are functioning properly. And that could lead to basically a problem in failure. So again, let's get right back to our worksheet and let's review what we've done so far. Some function is not being delivered. This is something we'd like to be able to check, would like to be able to prevent. Potential causes for this, in what different ways could this function stop? So for example, the engine doesn't work. In what different reasons are there why the engine does not work? What is the effect of it? Well, you can see right away what would be the effect of the engine not starting there. What is the severity? What is the impact of it? And then of course I've got some class, and that would depend on the severity class there, as I showed you earlier. Potential causes or the mechanisms of failure, this would be like your mode. And you do your cause and effect diagram there. Occurrence, this is again the probability of it. And current design control, do they do some prevention or do they do detection? And then detection rate, this is something that I've also got to figure out. So I have these three quantities: severity, occurrence, likelihood, and detection capability. These lead to my RPN, and the highest RPN would immediately get some attention there, so there will be some recommendation given to take care of this. Response and target completion date. These are there. Who is going to be taking that action there, and some other follow-ups there are there. So this is the worksheet that you should end up doing this. And I have these slides here, and these slides will be there. You can just flip through them up to a certain point. They will tell you what are the functions expected, what are the how failure modes are going to take place, how are you going to discover the effects of that failure there, how are you going to find out severity, how are you going to find the class, how are you going to find the different ways, causes of failure, how are you going to find the frequency of occurrence, how are you going to find the current design controls if they are there, how are you going to look at the detection capability, how are you going to calculate the RPN. This is something you'd like to be able to do. And of course, you want to be able to make sure that the high RPN items are there, all looked at before you go very further. And recommended actions, of course. This is something that you got to be able to end with when you end up with your FMEA. You got some FMEA actions there. Thank you very much. I really appreciate your spending time in browsing through these videos here. And we are approaching fast the end of this 40 session sequence of our lecture on Six Sigma. So the course will be ending with 2 more lectures, and there are 2 very interesting topics that are coming up for you in the next 2 lectures. So see you soon. Thank you very much.